Hello, physics class. This is Mr. Ng with a lesson about velocity and displacement and two new equations. Before we introduce the new equations, let's remind ourselves of the old equations. We have two for acceleration. Number one, acceleration is equal to velocity over time, or change in velocity over change in time. And we know that displacement is equal to 1/2 t squared, right? Let's rearrange this one so that it's in the form of v. So this means that v is equal to a times delta t, right? All I did was I multiplied both sides up here by t. The t's cancel. That means v is equal to a times t. So here, these two are our base equations, and I didn't really clarify this in the past, but these two equations only work if the object starts out not moving, meaning it only works if the initial velocity, initial as in the first velocity, is 0. If the object that we're observing is already moving, we have two new equations. This means that initial velocity is not 0. It's moving. So here we have a new equation, v final, this is like the final velocity, the final speed, is equal to v initial plus a times delta t. Notice that this is here already. We know that velocity is acceleration times time, and now we know that if something's moving, we just add that starting speed to it. Seems pretty easy. The final velocity is equal to the initial velocity plus acceleration times time. A similar kind of thinking occurs here. So to find that displacement, we just have to have the displacement from velocity. And we know that that's going to be v initial times delta t, right? Isn't that the velocity equation just kind of rearranged? This is going to find one bit of displacement. On top of that, another piece of displacement, 1/2 at squared. All right, notice this part is this part. And now we're just adding on a little bit where we multiply time and velocity to get that initial displacement. This will make a lot more sense once we start doing some problems. Let's dig through this sample problem. A plane starting at rest at one end of a runway undergoes uniform acceleration of 4.8 meters a second for 15 seconds before takeoff. What is its speed at takeoff, and how long must that runway be for the plane to be able to take off? Right, so we have a plane, right, and it's accelerating, right, and it's accelerating at 4.8 meters, this is an 8, meters per second squared, and it wants to know how fast is it right here? What's the v final here? And how long must this distance be? I have a quick little system to get us through this. It's called VVATX. VVATX. V initial, I'm going to put a little I there for initial. That's the starting velocity. V final, I'm going to put a little F there. Acceleration time, and this is our displacement, delta x. And let's go through this problem and fill in as many of these as we can. So the plane is starting at rest, meaning the initial speed is 0, right? It's staying still. Meters a second. The final velocity we want to know, so let's give it a question mark. The acceleration we have is 4.8 meters a second squared. And then we know the time, it's 15 seconds. And then our displacement we don't know. So we have a v, an a, and a t. And if I look here, this has an initial velocity, this has a time, this has acceleration and time squared. So we can use this one to find the distance. And look, we got a final velocity, that's our question mark, with a v initial, acceleration, and time. So we could use both these equations to solve these two problems. So let's start with number one. What is the speed at takeoff? Number one, the speed at takeoff is vf, right? vf is equal to v initial plus a times delta t. So our VF, we're just going to plug in our V initials right here. It's 0. Cancels out. Get out of here. Plus our acceleration, which is 4.8 meters a second squared, times our time, which is 15 seconds. So our final velocity is very simple. It's just 4.8 times 15. Let me get my calculator out here. 4.8 times 15, and I got 72 meters a second. Great. One part done. Let's do part 2. Part 2 wants to know the length of the runway. So we're going to use our trusty delta x equation. Delta x, displacement, is equal to v initial times time plus 1/2 at squared, right? I'm just going to ignore the deltas. That's just the amount of time that went by. Tired of drawing little triangles. Our v initial is 0, which means great. I get to cancel this whole bit because 0 times whatever is 0. So that means delta x is equal to 1/2 at squared. And we know this equation. It's the one we've been using for our reaction time lab. So delta x is equal to 1/2 times our a is 4.8 meters a second squared times our time, 15 seconds. This is all squared. Notice this becomes second squared. Here's second squared. So second squares cancel out. So we're going to be stuck in meters. So 15 squared is equal to 225 times 4.8 divided by 2. I got a delta x of 540 meters, or around half a kilometer. That's pretty far. So how did I solve this? Number one, I knew my two equations. Here they are. And then I made a cute little key where I identified my initial velocity, my final velocity, the acceleration time, and delta x. And then I just plugged in and solved. Let's try another example. A car with an initial speed of 6.5 meters a second. Oh, this one's a little different. We have an initial velocity. Accelerates at a uniform rate of 0.92 meters a second squared for 3.6 seconds. Find the final speed and displacement. So we're going to do our old trick, VVATX, V, V, A, T, X, V initial, V final, and delta X equal, 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 equal. So the initial speed is 6.5 meters a second. Our final speed, they want this. This is going to be our part 1, right? We don't know. Our acceleration is right here, 0.92 meters a second squared, 0.92 meters a second squared. And our time is 3.6 seconds, 3.6 seconds, but we don't know our displacement. So let's plug them in. So to find the final speed, again, we do VF, our final velocity, is equal to V initial velocity, plus A times T. VF then is equal to, I'm going to plug in V initial, is 6.5 meters a second, plus our acceleration, which is 0.92 meters a second squared, and the time is 3.6 seconds. So I'm going to plug that into the calculator. 0.92 times 3.6 plus 6.5, and I got my final velocity is equal to 9.8 meters a second. Good. Let's try another one, or the second half at least. So to find the displacement, I do delta x is equal to V initial times T plus 1/2 AT squared. Again, just plugging in. Delta x is equal to our V initial, which is right here, 6.5 meters a second, times our time, which is 3.6 seconds. Notice that seconds will cancel. We'll be left in meters, which is good. We're finding displacement. Plus 1/2. Our A is 0.92 meters a second squared. 0.92 meters a second squared. And again, time is 3.6, and I'm going to square that, second squared. Good. So I'm going to do some simplifying. my displacement is going to be 0.65 times 3.6, and I got 2.34 meters, right? That's just the velocity moving this thing forward. But what about how far the acceleration moves it forward? So 3.6 squared is 12.96 times 0.92 times 0.5 for a half. So I got 5.96 meters plus 2.34, and I got 8.3. So delta x is equal to 8.3 meters. Done. Again, I went through the problem, I identified all my variables, I made a nice key. So number one, identify the variables, and then I put it here into this nice key. I knew my equation, I plugged in, and then I solved. Awesome. I hope you're getting the hang of it. Let's do one last example before I set you off on your own. So here, an automobile with an initial speed of 4.3 meters a second, this is going to be our v initial, accelerates uniformly at a rate of 3.0, this is our a, and find the final speed and the displacement. All right, so this is our two question marks, and our time is 5 seconds. So again, I'm going to do v, a, t, x, v initial, v final, acceleration, time, and delta x. Our v initial is 4.3 meters a second. Our v final, we don't know, let's solve it. We need to have our acceleration, which is 3.00 meters a second squared. Our time is 5 seconds. And we need to know our displacement. So, part one, let's use our final velocity equation. Vf is equal to v initial plus a times t. V final is equal to 4.3 meters a second, right? V initial is right here. Plus a, which is 3.00 meters a second squared, times 5.0 seconds. Seconds cancel, so this is only meters a second. Our v final becomes, so I'm just going to type in 5 times 3, that's 15, plus 4.3. I got 19.3 meters a second. Great. Let's do part two. Part two, I'm going to use our displacement equation. Delta x is equal to VIT, the initial velocity times time, plus 1/2 AT squared. So our displacement is equal to our initial velocity, which is 4.3 meters a second, divided by the time, which is 5.00 seconds, plus 1/2 times A. A is going to be 3.00 meters a second squared, and then our time is 5.00 seconds. We're going to square that. So 5 squared is 25 times 3 is 75 divided by 2. So this little part becomes 37.5 meters, and then this front part is 4.3 times 5, and I got 21.5 meters. So our delta x is equal to just adding these two things together. All right, so plus 37.5, I got 59 meters. Okay, so part one, identify your variables, VVATX. Part two, pick the right equation, plug in, and solve. Thank you very much for watching. Good luck on your homework set.